Yeah, sorry. So then last class, we have started with this Maxwell velocities, RMS, V mean, and V probable. Other scans on. Just be careful with one thing here. Arca value is 8.3 joule mole per Kelvin. Don't use your chemistry ka Arca value. Perfect. Let's go ahead with few questions. Other scans on. So let's say speed of the molecules is given. One, two, two, three, 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 four. Yeah. So this is the speed of the molecules. Find V probable, find V mean and V RMS. Find V mean of oxygen at 300 Kelvin. If V probable of helium is equal to V RMS of hydrogen, find the ratio of temperature of helium and hydrogen. Get them all. Simple questions, just formula based. Hmm. Yeah, first was straightforward. V probable is the velocity which repeats a lot. You can clearly see 3 is repeating more times, so 3. V mean is simply just add them up. 1 plus 2 plus 2, 3, 3, 3, 3, 4, 4, 5 by 10. That is also coming to be 3, yeah? Whatever it is. What is VRMS? Same story. Square them. 1 square. 2 square will come 2 times. 3 square will come 4 times. 4 square will come 2 times. And then you get 1 5 square and the total by 10 and put a root. Then just put your numbers and you're done. What about B? Direct formula, V mean is equal to root over 8RT by pi m. So this is root over 8. R is 25 by 3, or you can put it as 8.3. Temperature is 300. Pi is 22 by 7. And molecular weight, this is what I'm more interested on. People write 32. Be careful, it is 32 into 10 power minus 3. So molecular weight, SI units must be in kgs. It is 32 grams per mole, isn't it, oxygen? You should be writing it as 32 into 10 power minus 3 kg per mole. Substitute there, you will get it. What about this thing? V probable is root over 2r temperature of helium by molecular weight is equal to root over 3r temperature of hydrogen by molecular weight. Square on both sides, r will cancel, and then you'll end up with 2 helium. Molecular weight of helium is 4 into 10 power minus 3. 3 into T2, and this weight is 2 into 10 power minus 3. Temperature of helium by temperature of hydrogen will be simply 3:1. 2, yeah, that looks fine. Clear with this? Direct formula substitute, there's nothing there. Any doubts on this? Just give me a minute. Let me just remove all the people whose cams are not on. And I don't know why last class I said, class is over and I'm talking and people are leaving in the middle of the class. I don't want to take names, but there are few people like, without even the class getting over, without listening to the instructions, first thing they shut down they just get out of the meeting. This is very irresponsible and it just tells you you're really not serious about this stuff. So yeah, please be, more aware. Until I say, you can go, please wait, read, listen to the instructions and whatever I'm talking about. Let's see one more. This is a good one. If 2 moles of helium at 300 Kelvin and 3 moles of hydrogen at 300 Kelvin are mixed, find VRMS. You have a mixture of gases. Now, what people do, I'll tell you. See. So VRMS is equal to root over 3RT. And here we will generally put molecular weight average. And the molecular weight average is given by N1, M1 plus N2, M2 by N1 plus N2. Now, be careful. This is wrong. This will not work here. Now, why is that? Let's see how that VRMS is actually calculated. Okay. First, let's take only one thing. Okay. If you just take VRMS of helium, now VRMS of helium is nothing but V1 square plus V2 square plus so on till Vn square by n ka root. So when you actually literally take all the molecules, I'll just put sigma Vi square. So this would be sigma Vi square by n. Agreed? Similarly, and this value is what we are writing as root over 3RT by molecular weight. So we will keep that anyway later on. Similarly, when you take VRMS of hydrogen, this is also root over sigma V, I'll write J, Vj square by, let's say M, because you can have a different number of molecules. This is the VRMS for each gas. Now you tell me, does VRMS care what gas are you talking about? It doesn't care about the mass, right? It will only simply count the speed of the molecule ka square by average. So when you take the VRMS of the mixture, it is simply V1 square, V2 square, so on till Vn square. This is for your helium plus V1 square, V2 square plus so on till Vm square by total number of molecules is n plus m ka root. Isn't this how you calculate? So this is for your helium and this is for your hydrogen. You just add up square of all the velocities and you finish it off. Now, if I just square on both sides for convenience, VRMS square mixture, this will be sigma Vi square plus sigma Vj square by n plus n. But what is sigma Vi square? Sigma Vi square, I'll square it here also on both the sides. I'll just remove the root. So sigma Vi square is nothing but n into VRMS square for the helium plus m into VRMS square of hydrogen by n plus n. Can you see the formula here? Now, if you try to substitute the VRMS value here, so this is the actual relation between them. If you try to actually put the values, you will end up with root over 3RT by pi molecular weight of helium m into root over 3RT pi, pi won't come, molecular weight of helium, molecular weight of hydrogen by n plus m. So if I take out root 3RT common, you end up with n by root molecular weight of helium plus m by root over molecular weight of hydrogen by n plus m. Does this in any way look like this? Can you see the problem there? If you take m average and if you look at this method, does they look equal? Do you get the problem there? They're not same, isn't it? So that m average method is wrong. You should not take molecular weight average. You literally have to go from the basics. You have to find the speed of all the molecules, square them and add them, and you do something like this. So the final result is this. VRMS square for a mixture will be number of moles into VRMS of the gas 1 plus N2 VRMS of gas 2 by N1 plus N2. Clear with this? To find the VRMS of helium separately, find the VRMS of hydrogen separately, and the number of moles are given 2 and 3. Just substitute this in the formula, you'll get the answer. So this will be 2 into root over 3R 300 molecular weight of helium, which is 4 into 10 power minus 3 plus 3 into root over 3R 300 molecular weight of hydrogen, which is 2 into 10 power minus 3 by total number of moles 2 plus 3. So be careful, don't use M average, it doesn't work here. And mathematically, logically, so na, when can you add things like that? When the functions are linear, isn't it? 1 and 2, see 1 and 3 ka average is 2, right? But 1 by 1 and 1 by 3 ka average is not 1 by 2. Do you get the problem there? So you just can't add up like that. So it doesn't work. It's a 1 by root m function. If the VRMS was proportional to m, it would have worked. because it's a 1 by root m function, it doesn't work. So be careful with that. You can't take m average. So that's what makes this question really good. All clear with this? Any doubts on this logic, please ask me. So there you just went back to the basics. You simply said there are n plus m molecules and each one had a different speed. So you just added them and you divided by n plus m. Why did it take same temperature? That is another problem. If you don't take the same temperature, then the mixture of gases, ka temperature itself will change, isn't it? They will come to an equilibrium and you'll get a new temperature. So that will get messed up.
Sir,
Yeah.
sir, how are you so sure कि the sum of the squares of the velocities for the mixture is equals to the sum of the squares of velocity for helium taken individually?
That I don't know, right? When you take the hydrogen and the helium molecules, both are at the same temperature, 300. I am assuming helium ka velocities are v1, v2, vn. हाइड्रोजन का वेलोसिटी सर v1 v2 vm मतलब सेम नहीं है ये v डैश ले लेना
हाँ सर, बट लाइक इसको आपने वो कैसे लिखा
क्या
जो पहले इनिशियली हमने जब सेपरेटली लिया था, तो इनके स्क्वायर्स का सम और उनके स्क्वायर्स का सम इक्वल कैसे है?
if I just ask you what is the VRMS of the hydrogen gas in the sample, won't you just take the velocities of the hydrogen molecules only?
सर आई थिंक वी वोंट बी एबल टू कमेंट ऑन दैट।
क्यों?
सर क्योंकि वो मिक्सचर है एंड लाइक इट मे बी डिफरेंट, समथिंग मे
Why?
बी हैपनिंग।
Normally VRMS का क्या आता 3RT by m, that does not change for a single thing. See, VRMS is a hypothetical thing you created. Now, what does VRMS tell you? That is a velocity where your total energy becomes equal. Bus, it's a thing, what you're assuming is VRMS, matlab, the molecules don't know what is VRMS. It is you and I who are talking about VRMS, isn't it?
ओके।
For a given temperature, the molecule will have same kinetic energy. Makes sense?
ओके सर।
So think of like that. Next one. Now, let's say instead of Maxwell distribution, we have a hypothetical distribution here. NV, which is dn by dv. I'll just write it NV, I'll write separately here. So this is NV versus V graph. And let's say this is a parabola. Hypothetical distribution. So let's say the molecules are distributed in terms of like a parabola, and this is V naught. So here, the speed distribution of gas molecules versus V is a parabola. So that n subscript V is simply the number of molecules with a speed range of dV. N naught is the total number of molecules. First question, find the equation of this curve. Meaning I want the equation between NV and V. Find V probable. Find V mean. Preferably try to get them without solving. Find VRMS. VRMS के लिए you have to do some work. And I hope you remember VRMS का general formula is what? Integral form is this, everyone. Integral V square dn by integral dn का root. In case you forgot, I'll just write it down again. Yeah, VRMS, V mean and V probable you can see and tell. Get the equation, that is all pure math. Nee, Shreyans, what did you even exactly write? It's a parabola. Get me the relation, right, between NV and V naught. I know, you know the two roots, so you guys just took like x minus a into x minus b is equal to constant, but what is that constant? You have to take that also.
Sir,
Yeah.
sir, is the parabola like monic polynomial? So मतलब
It's a
leading
regular,
coefficient is zero.
it's a regular parabola. I don't know anything more than that.
Sir, I'm asking कि like ax square होता है ना plus bx
I
plus तो
don't
a
know.
equal to 1.
No idea. बस इतना ही दिया था क्वेश्चन में.
Okay, sir.
I don't know what kind of parabola it is. All that in it looks like an inverted parabola. I'm a layman in Max. I'll simply call it a parabola which is looking down. Thus, you can call it however you want. It's a cupped parabola. Up to you. Did everyone find V probable? That was the easiest one. What is V probable? The point where the maximum number of particles are. Isn't that exactly the midpoint? So V naught by 2 is the V probable. The velocity which is having, at which your maximum number of molecules have that speed. So NV is maximum exactly in the center. It's a parabola. So yeah. What does V mean? You can tell that also without calculating. Anyone? Right, Utsa. नहीं आती. V mean is average, रे. Right, Arya. You can see the equation and you can figure out V mean without solving anything. Right, Samyak? Tell you. See, if you look at the center, because it is symmetrical, if these molecules have speed V naught by 4, you will find the same number of molecules here with 3 V naught by 4. The average of these two is V naught by 2, isn't it? For every molecule on the left hand side, you'll find another molecule on the other side whose average will always come out to be V naught by 2. Make sense? I agree. The number of molecules are different, but you have the same number of molecules on either side. So the average velocity of all the molecules is V naught by 2. So V probable and V average both are same in this case. Got it? So that is how you can figure out. And how to get the equation, everyone, start with this. Y is equal to ax square plus bx plus c. Or if you know any better way of finding an equation, figure it out. What is y? Nv. A, I don't know. What is x? V square. Bv plus c. We have two constants. When v is 0, nv is 0. When v is v naught, nv is this thing. And area under the curve is n naught. There you have three equations and three variables. You can figure out a, b, and c. The area under this curve, which is integral nv dv, must be equal to n naught. That's the total number of molecules. Try. I'll give you a minute or two. So what V probable and V mean are easy. You can see until. Yeah. 3 n naught by 2, 1 minus V square by V naught square. नहीं रे उसमें दो टर्म्स आएगा. You will get a term like AB minus BV square ऐसा कुछ आएगा. Let's get this. So this point here, this is V naught by 2. This is your NV max. So V probable is V naught by 2. And then you can also argue like this, for every one molecule that you have here, V1, and if you take a symmetrical point here, this will be V naught minus V1, right? So the average will be V1 plus V naught minus V1 by 2 is always V naught by 2. So you have equal number of molecules on either side. So we can do this for all molecules. On either side of V naught by 2, right? So they give an average. So therefore, V mean is also V naught by 2. Maxwell distribution with this does not happen because this is a hypothetical curve, it happened. Then we need to find the equation. So since it is a parabola, y is equal to ax square plus bx plus c. This is your general equation. So this is nothing but nv. A, x ka place mein we have v square, bv plus c. When at v is equal to 0, nv is equal to 0. That's your initial point. So therefore c is equal to 0. So we got c ka value there. And then similarly, when v is equal to v naught, then your nv is also again equal to 0. So this will be a into v naught square plus b into v naught. This is your equation 1. How to get the second part? The area under the curve integral nv dv will give you the total number of molecules. Let me show it in the next page. So we know nv is nothing but dn by dv, which is a into v square plus b into v. So we still don't know a and b there. So when you try to integrate this, integral dn is nothing but av square plus bv into dv. Limits will go from 0 to v naught. This must tend to be n naught. I'll just write like this, n naught. Integrate this thing. So this will be av cube by 3 plus bv naught cube, bv naught square by 2. This is your equation 2. So you have equation 1 and equation 2. Equation 1 is this guy. Av naught square plus bv naught is equal to 0. And this is your second equation. Get b ka value from here, which is minus av naught by b is, yeah, that minus bv naught. Take this and substitute here. Av naught cube by 2 is equal to n naught. This would give you a is equal to 6n naught minus by v naught cube. And b is equal to av naught, so that is 6n naught by v naught square. Therefore, your equation nb will be minus 6n naught by v naught cube v square plus 6n naught by v naught square into, this is the equation of that particular parabola. Again, I did nothing except little math there. Check it out. Right, Anvita. I think that looks right. All clear with this? Param.
So can we also do this like using maxima, because we know the maxima is like v naught by 2.
Do it now. I'm saying, right? I just showed you one way. You guys are pros in maths, though. You guys have done parabola big time. So I just want the ND equation. Get it however you want. I guess it's not a physics question. You can do that also. It works. Clear with this? Once you got the equation, abhi kya karenge? You have to find VRMS. Get it? I'll give you a minute. What is VRMS ka formula? Integral v square dn by integral dn ka root. And what is nv here? Nv is nothing but dn by dv. So get dn from here and substitute there. Right, Aditi? Anyone else? So let's just substitute there. VRMS square is integral v square dn by integral dn. So this is v square and dn is nothing but, yeah, that big one, minus 6n naught v square by v naught cube plus 6n naught v by v naught square dv. This will go from 0 to v naught, and denominator you can just put n naught. There's no need to solve, that's the total number of molecules. I think if you solve this, you'll end up with 3 by 10 v naught square. You'll get VRMS will be root over 3 by 10 v naught. Check your answer. That's what you should get. Right, Anita. That is simply x power n ka integration. That much you guys can handle. Have a look at this. Right, Utsa. Clear with this? There's nothing there. It is just math. You get Tn is this, substitute there, and you're done. So if at all they try to play around, right, this is what they will do. They will give you some arbitrary equation and they'll expect you to find the RMS value. So that is how much they can play around. So not much on this. Clear, no? Everyone? Shaurya? Tanishka? Clear? Arya? Devanshi? Rudransh? Srihari? Clear? Yashvi? Vanshika? Yashvi? Clear? Great. Next thing, degrees of freedom. If you remember, I talked about something like this even in rotational mechanics. Degrees of freedom, we will use a symbol small f. It is simply the number of independent ways a system can possess energy or motion. So then we have a law, it's called law of equipartition of energy. So what this thing says is the energy associated with a molecule right, is equally divided among its different degrees of freedom, and each degree of freedom has an energy of half kT. Where K is your Boltzmann constant. Which is given by the gas constant R by Na, the gas constant by Avogadro number. Let me write it like this. Which is 8.3 joule per mole Kelvin. Avogadro number is 6 into 10 power 23. So this K value comes out to around 1.38 into 10 power minus 23. That's your Boltzmann constant value. So this is a theorem there, like, it will tell you always that energy is equally distributed among different degrees of freedom. Now, that again comes from, the random motion only, because the molecules are moving in every direction and we have a large sample. You can say almost, that velocity in X direction, Y direction, Z direction will be same. And for some reason, right, even the rotational components also will be same. Now that is a little weird, but yeah, but this actually theorem works really well at low temperatures. But as you start increasing the temperature, it actually starts going wrong. So we'll not get into that, but that's a theorem there. So the kinetic energy of a molecule, from this theorem, each degree of freedom is giving you half kT. So you have F degrees of freedom into half kT. This is the kinetic energy of one molecule. Now the total energy of a gas, kinetic energy of a gas will be total number of molecules into kinetic energy of the molecule. Total number of molecules are nothing but N into Avogadro number of moles into Avogadro number, and this is F by 2 kT. Na into K becomes nRT. The formula becomes F by 2 nRT. This is the kinetic energy of the gas. So be careful. Kinetic energy of a molecule is different. Kinetic energy of a gas is different. So what is the internal energy of a gas? So this is the thing for thermodynamics, basically. So internal energy is nothing but kinetic energy plus potential energy. But we take potential energy as 0 because there is no interaction in ideal gas. That means the total energy of a gas or internal energy of a gas is simply the kinetic energy, which is F by 2 nRT. There, this is the kinetic energy of the molecule. This is the kinetic energy of the gas. This is your internal energy of the gas, which is same as the kinetic energy of the gas. Clear this? Now, how do you find the degrees of freedom? For monatomic, helium, argon, these kind of gases. The molecule can go Vx, Vy, Vz. And technically speaking, it can also have one rotation. But then we said size of the molecule is 0. Size of the molecule tends to 0. So the moment of inertia I, which is 2 by 5 mr square, will also tend to 0. Therefore, the kinetic energy of the rotation half I omega square will also tend to 0. So this is negligible. We ignore this. So a monatomic will only have 3 translations. So for monatomic, F is equal to 3. Diatomic, H2, oxygen, nitrogen, these kind of molecules. Vx, Vy, Vz, we have 3 translations. And you can rotate like this. You can rotate in this plane. You can also rotate in this way. But again, same story for this. This is negligible because the axis is passing through the molecules. I will be 0. So basically you have 2 translations and 2 rotations. 3 translations and 2 rotations. So here F will be 5 at low temperatures. Even for molecules like, the linear triatomic molecule, something like carbon dioxide, CO, even for this it is 5 because you can see that atom carbon dioxide, right? The bonds, right, are perpendicularly locked. It cannot go in any other direction. It just kind of behaves like a rod only there. So even for this, F is 5. I'll give you a table on all these degrees of freedom. Clear with this? Now, if you increase the temperature, something happens here. The molecules will start vibrating. They're already vibrating initially, but we ignore that normally at low temperatures. So they will mention in the question, you'll understand, temperature is high, so he is expecting you to take an additional degree of freedom. Molecules vibrate. Think of like, when you have 2 molecules with a bond, think of like this thing. We have a block with a spring. So here the molecules are vibrating, so we have vibrational kinetic energy. So this is called a vibrational mode. And one vibrational mode has vibrational kinetic energy and vibrational potential energy. Half kx square and half mv square, something of that. So one vibrational mode has 2 things. So if you have n vibrational modes, will imply you have 2n vibrational degrees of freedom. So this is a question they asked in JEE. For polyatomic molecule, has 2 vibrational modes. And the question was find adiabatic constant. So this thing has 3 translations, Vx, Vy, Vz. Now polyatomic, right? It is not diatomic. So all 3 rotations are possible. They have 3 rotations. And each vibrational mode is 2 into 2 vibrations. So total this thing has 10 degrees of freedom. That itself is a straightforward question. Once you know the degrees of freedom, you can find gamma from there. So be careful with that. So at high temperatures, the molecules will start vibrating, and that will create you something called a vibrational degrees of freedom. And each mode will give you 2 vibrational degrees. Making sense, everyone? So let me show you the table there. This is from NCERT directly, so we will mug it up. We will need this again in thermodynamics. There are small things I need to change. So look at this thing, monatomic, F is equal to 3. You have 3 degrees of translation, 0 rotation, 0 vibration. Triatomic linear, again 3 translation, 2, and this thing. This is a triatomic non-linear, so 3 translation, 3 rotation. So this is F is equal to 5, this is F is equal to 6, and this is F is equal to 7. Here you have to be careful. This is this is 2 degrees of freedom. This is 2F, 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 2F. Now let's do one thing. Let's take it as N basically. N vibrational modes. So N vibrational modes will have 2N degrees of freedom there. Basically, the way it is written, right, in NCERT is like one vibrational mode has an energy of kT. So basically half kT, 2 kT. So this is 2. This is 2 by 2. Sorry. 2N, 2N by 2. This would be N, this would be N, this would be N, N, and N. Yeah. Clear with that? So that's a small correction there. So be careful there. So one vibrational mode has an energy 2 times half kT. So they write it simply as kT. That is the reason you can see that kT there directly here. You should definitely remember this thing. All clear with this? Next thing. Suppose if you have 2 gases mixed up, average degree of freedom F average is given by N1, F1 plus N2, F2. It's a linear function. If you see U is proportional to F, so you can directly do this. Example, if you say 2 moles of helium and 3 moles of oxygen, 3 moles of hydrogen. If they don't mention anything, take low temperature. They are mixed. We have F average, helium का 3, hydrogen का 5 by 2 plus 3. That is 6 plus 15, 21 by 5. Now, there's another way of writing this kinetic energy. We know PV is equal to nRT. So we can write this thing as 2 by 3 into 3 by 2 nRT. So we can write 3 by 2 nRT is nothing but 3 by 2 PV. This is nothing but the kinetic energy, translational kinetic energy of a gas. Any gas. Because for all gases, the translation component is only 3. So this is another way of writing the same stuff. Okay with this? So just to brief up all those things that we wrote, the formulas. Kinetic energy of a molecule, F/2 kT. Kinetic energy of a gas, F/2 nRT. Kinetic energy translation of gas, basically F becomes 3. Kinetic energy of translation of the molecule is 3/2 kT. The same stuff, I'm just putting it down. There, that's about your degrees of freedom. Okay with this? Let's see some questions. This is a good question, sir, theoretically. So listen carefully. Let's say we have two gases. We have N1 moles hydrogen or helium, N2 moles hydrogen. They have same temperature. Find the ratio of kinetic energy of the helium gas by kinetic energy of the hydrogen gas. Find the ratio of kinetic energy of the helium molecule. Find the kinetic energy of the hydrogen molecule. Find the ratio of kinetic energy of the molecule translation. And find the ratio of kinetic energy of hydrogen molecule translation. There, get these ratios. So we have two containers filled with N1, N2 molecules, helium and hydrogen, same temperature. Find the ratio of these three things. Get it? Simple formula substitution. Let's give it a try. Right, Param? नहीं आदिति. Right, Shreyansh. Try, everyone, try. I'll give you a minute. Right, Samyak. नहीं आ रही. Second one क्या वो?
नहीं सर, थर्ड वन.
Okay. Get the first one record. वो
सर
छोड़
जो
के
पहले
directly.
लिखा वो किया.
So what to do here? Again, look at the formula here. Huh? What is the kinetic energy of the gas? Kinetic energy of the gas is F by 2 nRT. Means this is proportional to F into N. So this would be F helium, N helium by F hydrogen by N hydrogen. That would be 3N1 by 5N2. That's it. What is kinetic energy of a molecule? The kinetic energy of a molecule, it is F by 2 kT. So this is proportional to F. So this is 3:5. What is the kinetic energy of a molecule? Translation. Now for any molecule, the translation will always have only 3 components. So that is 3 by 2 kT. So this is 1:1. Make sense? Whether you take hydrogen or helium, the translation components are only 3, right? So be careful with that. Total energy is different, translation kinetic energy is different, and energy of the total gas is different. Total energy of the gas will depend on the number of molecules. Kinetic energy of one molecule will depend on the degrees of freedom, whereas the translation kinetic energy of one molecule is independent of anything. It depends only on temperature. Clear with this? This is what I was saying earlier. RMS में, if you see na, at a given temperature, the kinetic energy for a molecule is same, but the speeds are not same because masses are different. So when you mix up two different gases, that particular speed ka ranges will be same only, na? V1 square, V2 square, Vn square.
Okay, sir.
That average. All clear with this? Easy one. But yeah, you need to know the formulas for kinetic energy of a molecule and a gas and everything. Let's see one more. We have two compartments. Pressure is P1, volume V1, temperature T1. This is a hydrogen gas. P2, V2, T2, helium gas. And you have a stopper in the middle. Now, if you remove this stopper or a tap, the gases get mixed up completely. Find the final pressure and final temperature. These containers are insulated, okay? So heat cannot go out or cannot come inside. Find the final temperature and the pressure when the tap is opened. There, let's get this thing. Try, everyone should give it a try. It's a good one. It's a good mint level question. Give it a try. How do you find? So what remains constant? Number of moles. What else remains constant? Total energy. because the whole thing is insulated, there is total internal energy must be constant. Start from there, you'll get it.
Can you show the formula of F average again?
N1 F1 plus N2 F2 plus N1 plus F2, no? N1 plus N2.
Okay, sir.
Shaurya, just tell me temperature. If you got that, then I know you got it. Okay, let's see. Someone who did actually type everything. Spy P1, P1. Okay, let's see. So, finally, when you open the tap, the whole thing will get dispersed. The final pressure is P, final temperature is T, final pressure is P, final temperature is T. So we can write the final pressure into volume, which is V1 plus V2 is equal to N1 plus N2, that is the total number of moles, into RT. This is your equation 1, comes from ideal gas equation. What is the number of moles? P1 V1 by RT1. What is N2? P2 V2 by RT2. Make sense? That's your initial number of moles. Now, if you see, we actually have two variables, P and T. The second thing, conservation of energy. So what is the initial energy of the thing? N1 F1 R by 2 T1. So that is the formula for the gas. F1 by 2 N1 RT. So let me write it that way only. F helium, left was hydrogen actually. F hydrogen N1 R T1 by 2 plus F helium N2 R T2 by 2. This is your initial energy, must be equal to F hydrogen N1 by 2 R T final plus F helium N2 R T final by 2. R by 2 will cancel everywhere, and that will be 3 N1 T1 plus 5. No, this is 5. 5 N1 T1 plus 3 N2 T2 is equal to 5 N1 plus 3 N2 T. Therefore, your final temperature is 5 N1 T1, 3 N2 T2 by 5 N1 plus 3 N2. You know N1 and N2 values, you can substitute there. You will get it. Yeah, I think that will come in terms of like 5 P1 V1 plus 3 P2 V2 by 5 P1 V1 by T1 plus 3 P1 P2. Yeah, it's a little lengthy. But clear with this. Right, Aditya. I think you might be right, Param. All clear with this? There. Take a break. Come back in 9:42. We'll continue from here. We're almost done. There's a little part left, and after that, we'll start off with thermodynamics introduction. That will be better, more fun. Come back in 5 minutes. Take a break. Sure, let's start off. Now, this next thing is important. Mean free path. I'm sure you've done this in chemistry, but let's see. And this thing, now, mains may every year out of that 8 or 10 sessions, you will find this question in 1 or 2 sessions. Before 2020, literally every year they used to ask one question from this. 2021, 22, half of the sessions used to come. So what is mean free path? Again, we don't have the derivation here. Mean free path is your average distance traveled by molecules between two consecutive collisions. So lambda is given by 1 by root 2 pi sigma square NV. Sigma is your molecular diameter, other scans on. This NV is simply number of molecules by volume. This is also called as number density. You should remember the formula. Then we define something called relaxation time. Tau. So relaxation time is simply the average time interval between two consecutive collisions. Now think about this. What is time? Time is simply the distance traveled by speed, isn't it? So relaxation tau is nothing but lambda free mean path by v mean. So separately, no need to remember the formula. If you know free mean path, you'll get this thing also. 1 by root 2 pi sigma square nv v mean. And v mean is root over 8 RT by pi m. So this tells you what is the time interval between, again, an average time between two collisions. Now, if you're colliding, if the time interval between two collisions is 0.1 second, that means in 1 second, how many collisions are happening? 10 collisions per second. So we define something called collision rate. It is given by Z. This is simply number of collisions per second. This is 1 by tau, which is root 2 pi sigma square eta v mean. You can put on the formulas in the red box. You will need them. Sigma is your molecular diameter, eta v is your number density, v mean is your average speed. Clear, Rita? Great. Let's see a question. Now, these questions are actually PYQs, huh? Consider an ideal gas confined in an isolated glass closed chamber as the gas undergoes an adiabatic expansion. Now, we still didn't do adiabatic, but this is the formula. PV per gamma is constant. You must have done in chem. Or we can also write TV power gamma minus 1 is equal to constant. Gamma is your adiabatic constant, Cp by Cv. So then he's asking, the question is, find the average time interval of collision between the molecules increases as volume power Q. Then find Q. This was a 2017 PYQ. Old ones, but give it a try. If you don't know the formula, you can't do this thing. It is straightforward. So if you know the formula, it is just a matter of manipulating it. And D is not the answer. There, in case you don't know the formula, again, this is what I'm asking. Tau, average relaxation time. 1 by root 2 pi sigma square NV V mean. Everyone, give it a try. I'll give you 1 or 2 minutes. It's important. If you got one model, then you're done. Matlab, kuch hai hi nahi. You will understand how to do this. But give it a try for one question. I'll give you a few more. There are 4 options. You can just say na, A, B, C, D. Why are you creating new options? No, that is wrong. Right, Aditi. But guess mas maro. Right over here. See, you're asking for tau. So tau is equal to 1 by root 2 pi sigma square NV V mean. So this is proportional to, so this is 1 by root 2 pi sigma square. NV is simply number of molecules by volume. V mean is root over 8 RT by pi m. So we can clearly see tau is proportional to volume by root temperature. That is the main thing. You need to get in terms of volume and temperature. But we also know Tv per gamma minus 1 is constant. So from here, we know T is proportional to 1 by V power gamma minus 1. Take this and substitute here because you're trying to replace everything in terms of volume. So we get tau is proportional to V by, this is 1 by V power gamma minus 1 by 2. So that will be V power 1 into V power gamma 1 minus 2. So proportional to V power gamma plus 1 by 2. First option. Clear what we did? So basically in that NV, there is a number of molecules by volume. There is one volume sitting there. And V mean may root air T by pi m. There is a temperature there. So, and since an adiabatic process, Tv per gamma minus 1 is constant, replace the T with volume and you're done.
So like in these type of questions, it's very important to learn the formula, I guess.
वही तो बोल रहा हूँ. Remember the formula, remember the formula. There's nothing there. Let's see one more. These are actual JEE Mains ka questions.
So much formula.
Do you say the same thing to your chemistry also? Your chemistry teacher will kick you right and left. Get this thing. I think ये 2019 है 2023 का है. Session 2 2023. Let's get this. You need to remember a certain amount. People think, itna ratta maar raha hai, but if you don't remember things, then you won't have enough knowledge, for your brain to connect things. That is how thinking works. If you want to become an architect, what do? You go and study 100 different buildings. You literally ratta maroge. Matlab har building mein kya kiya. And when you have enough knowledge in your brain is always trying to connect to them. And that is how you get new ideas. When you don't have any knowledge, where you get ideas from? Ideas are simply accumulation of knowledge in different things. And that is the reason, normally what happens, right, in big industries, a newcomer, right, who is completely from a different field, sometimes will succeed, rapidly compared to people who are already there in the same industry. Happens a lot because they can't think outside the box. There was this guy, who wanted certain things to be delivered. So, but all these deliveries by ships and everything, right, was very slow. Then this guy, started a small service where you do deliveries by planes, and people started laughing at him. He said, "Who the hell will take deliveries in planes, and who will actually do shipping in planes?" And that guy didn't listen, but he started. He's actually from a very something industry, and that company is called FedEx now. And there is this one guy who went to Ferrari and told them, "Boss, your cars are very good, but brake me, there is a problem." And the Ferrari owner, right, laughed at him and said, "What do you do exactly?" He said, "I'm a farmer. I have a tractors. I run tractors." The Ferrari guy said, "See, boss, you stick with your tractors. I will stick with my Ferrari. So you don't tell me what to do." That guy got so pissed off. He went back and he said, "I'm going to build cars from today." That's where you get from Lamborghini from. So that is how things work. You never know. What is the answer for this guy? Okay, option 4. Option 1. I don't know itna cars kara. I just know little. You guys are pros actually. Paganini, Giganini, some numbers. Names you're giving, I have no idea.
The
Movie भी
same
आया था
thing,
ना.
yes, sir. So the same thing happened with Pagani. What happened with Ferrari and Lambo, and Pagani के साथ जो हुआ वो Koenigsegg के साथ हुआ.
But who is Pagani? I don't know actually.
And there is one guy who owns car, like
Okay,
who builds cars.
that is also cars only. क्या? ठीक है. I am really not that into cars, so I have no idea.
And like
Anyways, next thing.
जो Ferrari था उसका भी हुआ था Ford के साथ.
वो होता रहता है. छोड़ दो. Let's see. So what is this thing? So ideal gas is there in a cylinder. Again, same story. You're asking for the mean free time. Tau is equal to 1 by root 2 pi sigma square NV. Mean. Again, same story. Nothing there. So this is proportional to 1 by root 2 pi sigma square. This is N by volume. 8 RT by pi M. So this is proportional to volume by root T. But if you see in the question, everywhere they're talking about pressure and temperature, means this time you don't want volume. So from ideal gas equation, PV is equal to nRT, eliminate volume. So V is proportional to T by P. If you bring this and substitute here, this will end up with root over T by P. बस यही करना था. So tau 1 by tau 2 will be root over T1 by T2 and P2 by P1. So tau 1 is 6 into 10 power minus 8. This is tau 2. The root T1 by T2 is 300 by 500. And the pressure has become doubled. So P2 is 2P by P. So all this you will end up with 3 into 10 power 8 by root 5 by 3. That's close to 4 into 10 power minus 8. If you say 10 power minus 8, there are only two options. And the one which is closer to 4 is this guy. And so if you see, there's no need to actually solve. You just have to have a rough idea exactly what will be the value there. All clear with this? Again, not a tough question. As long as you know the formula and you know what you have to substitute, you're done. Let's see one more. I hope this was clear. Since you're talking about pressure and temperature, replace everything in pressure and temperature. The next one is a good one. Let's get this. Two gases, argon and xenon, at same temperature have same number density. Same number density. That NV is same. The diameters are given. Find the ratio of their mean free time. Okay, let's see. Option C, option A, option B. What do you guys think? Let's see. So what makes this question good, right? People do this thing. They're asking for mean free time, so tau is equal to 1 by √2 pi sigma square v mean. So people think, okay, you said same temperature, and you said the molecular diameter is changing, so sigma is different here. So this is the catch here. √2 pi sigma square NV is equal grade. This is root over 8RT by pi molecular weight. This is proportional to root molecular weight by sigma square. Just because temperature is same, V mean is not same. They have different molecular weight, isn't it? So there is a molecular weight sitting in the V mean here. NV is same. So this number density is nothing but NV. So most people ignore that molecular weight. They simply write it as 1 by sigma square. So just be careful with that, nothing much. If you figured it out, I think then you're on the right track. Then the mean free time of argon by xenon is root over molecular weight of argon by sigma square of argon, sigma square of xenon by root molecular weight of xenon. That turns out to be root over 40 by 131, and this is 0.10 by 0.07 ka square. That would be 100 by 49, and this would be 40 by 131. That's roughly 2. 40 by 130, so that's roughly around 4 by 13. So that will be again, one more 2 will come out. So that's 4 by root 13. One thing is clear, this is definitely less than 2, isn't it? This is definitely less than 2. It is slightly, little greater than 1, and there is only one option. So yeah, this is the answer. Aditya has become pro in guessing. Yeah, option 1. Clear with this? If you have not taken that option 1 right, you will get answer 2. I know exact numbers are not matching, but yeah, something like that. So be careful with that. So the catch here is the molecular weight. Most people forget that. Clear with this? There. With that, we are done with KTG. Today, I'll send you a sheet on thermodynamics on everything like thermal expansion, calorimetry, KTG. It's a pretty good sheet. The questions are really good ones. They're from that Rizoka sheet, so you can give it a try. Some of the questions will be repetitive from somewhere. But the questions are, it's all collected at one point, so it'll be a good practice if you can try that. That should give a good practice. Great. Next thing, thermodynamics. Like I said, thermo and heat transfer, these are the two main chapters, advanced perspective. Again, certain things will look similar to chemistry, but there is one or two things which are a little also different. That's where you have to be careful. The first thing, zeroth law of thermodynamics. So what is this exactly? If two isolated systems, A and B, are in thermal equilibrium, if systems B and C are in thermal equilibrium, then A and C are in thermal equilibrium. Kind of looks obvious actually. Indirectly, if you see what they're saying. If A and B have same temperature and B and C have same temperature, then A and C have same temperature. Isn't that what it is being said? And that is the reason people didn't think it is actually a law. So first law came, second law came, and then they realized, see, whenever you say it is obvious, it should be obvious for every property. That is when it is obvious. I'll tell you what it means. I'll give you a crude example. So think of like this. If A and B are friends and B and C are friends, is there any guarantee A and C are friends? Right? Suppose A is going with velocity V, B is at rest, C is going with velocity V. A thinks B is moving, C thinks B is moving, but A thinks C is at rest. So that means this particular thing is not valid for velocities, isn't it? You're getting, so there are certain properties for which this statement does not work. If A thinks B is moving and B thinks C is moving, then A thinks C is moving. So it doesn't work. So it's not really obvious. It works only for a certain kind of properties. And heat is one kind of a property, temperature, where it actually works. So people said, boss, this is a different property actually. So you just can't say it is obvious because it looks obvious, but yeah, it is not, because it doesn't work for every property. Clear with this? So that's what we call it as a zeroth law. It just tells you about the equilibrium condition and temperature. So there's nothing much on that. So the first law of thermodynamics, this is where we'll spend maximum time. We do also have second law, but only for heat engines. Again, we'll not get into all the definition stuff. We'll put it on directly. So first law of thermodynamics is simply dq is equal to du plus dw. Be careful here. Unlike chemistry, right? I think in chemistry it is dq plus dw is du, right? But physics may it is dq is du plus dw. So be careful with that convention there. So dq is the heat given to the system. Du is your change in internal energy. I hope right now no one is being taught thermodynamics in chemistry. That would be a disaster. It happened once when I was in Hyderabad long back. I was teaching thermodynamics. Every day the students used to mess up the sign convention. Every day. After 2 days, I got so pissed off. I was telling them, boss, aap log kar kya rahe ho? What kind of mistakes are this? Then I went to the staff room and the chemistry sir is also shouting on them. What kind of mistakes you're doing, idiots and all. Then I was telling him, sir, these people are not remembering basic convention. He said, then he asked me, like, Arun, what chapter are you doing? I said, thermodynamics. He said, shit, I'm also doing thermodynamics. So physics and chem both started thermodynamics at the same time. The convention it is messed up. From then we made a rule, like, when physics and chemistry people are teaching, we'll keep at least 3 months gap. So we don't do it at the same time. But yeah, be careful with that. I think the whole thing, in my entire teaching thing, the biggest blunder I did was in one batch I was teaching integration, in one batch I was teaching differentiation. I went to the differentiation ka batch and taught them all integration ka formulas. And the class went on for 20-25 minutes. And then I realized, shit, what is this? Meaning, I did this. It's a d by x power n is x power n plus 1 by n plus 1. This is what I taught. This is my first year of teaching. 2011, yeah, 10th. 11 ka first, yeah, starting. And then I had to say like, oh shit, karke. Then I had to tell them to cancel everything, and then I have to do, and then again decided same thing, boss. I should never teach differentiation integration in two different batches at the same time. Certain things you will learn from experience. There, so if you actually think about this formula, right? Think of like this. I'll give you heat. It's like I'll give you some money. Either you store the money or you use the money. That's it. You buy something or you save it. That's it. You have only these two things. So basically, the first law of thermodynamics is another form of law of conservation of energy. Now, the important thing, the sign convention. This is important because you mess up a sign and the whole thing will go for a toss. Now, how do you remember this thing, right? Think of like this. In physics, you're more interested in heat engines. So if you have an engine, what are you expected to give? You're expected to give heat, and in return, you expect work, isn't it? So keep that in mind when you think about the sign convention. So if heat is given to the system, you want to give heat to the engine, that is positive. If you give heat to the system, we take it as a positive heat. If heat is rejected by the system, so if the system gives you heat, you don't want the engine to give you heat. Heat rejected by the system is negative. So think about the heat engine, so that will keep your convention easy there. Work done. Now you tell me again, do you want the engine to give you work or take work? Do you want the engine to give the work? So work done by the system. So this is reverse in chemistry. Huh? Work done by the system is negative in chemistry. But for us it is positive because you expect the engine to give you. And if you look at the formula, you'll understand why now. The dW is on this side, no? So when you bring it this side, you'll get the minus sign. Are you clear? So work done on the system. So you don't want to give work to the system. You expect the engine to give you work is negative. So just be careful with that convention there. And the first law also has a drawback. It does not tell us the direction of the reaction. The first law simply tells you as long as the energy is conserved, the reaction can go any way it wants. It does not give us the direction of reaction or direction of process. So first law assumes as long as the energy is conserved, it doesn't matter. The reaction can go anywhere it wants. If you take an example from chemistry, if you take sodium hydroxide plus HCl, you get salt, you get water, and you get some heat. 14.7 kilocalories. Now, if you see this reaction proceeds, but what the first law thinks, NaCl, if you put salt, if you put water, and if I give heat, it will assume you're going to get your sodium hydroxide and HCl again. And this is not going to happen. This is where the second law comes. The reaction proceeds in the direction of increasing entropy. Do you guys remember that? So that is where the second thing comes. So that's your second law. Now we'll not get into this right now. The process goes in the direction of increasing entropy. So entropy tells you whether the reaction proceeds or not. We do have it, but in physics it's a very small bit, but chemistry you have a lot. If you're doing electrochemistry, it comes there also. It gets mixed up everything. Thermodynamics, electrochemistry, it's a thing. Clear with this. So now what we are going to do, we are going to study the three terms properly. The heat, the delta U, and this thing. And luckily we have already done all this thing. So the first thing is the heat. Where did we do this thing? Calorimetry. Heat is Q. So dq is ms dt. We use this for liquids and solids, or NCDT. We use this for gases. So we define the molar heat capacity is the amount of heat required per mole per unit change in temperature. Important. Later on, we're going to define molar heat capacity for different processes like isobaric, isochoric, polytropic, and all that stuff. How did you know 14.7? Chemistry में था ना 14.7? Ionic equilibrium में? No? I thought 14.7, 13.7. I don't remember the number. ठीक है. We will just write it as heat. Happy, since you don't like numbers. 13.7, yeah. ठीक है. Now, if you look at this thing, right, that is about your heat. Next thing is your internal energy. Where did you learn this thing? We just learned about this thing in KTG. So internal energy is nothing but kinetic energy plus potential energy of the gas. But we know the potential energy is zero, since molecules do not interact in an ideal gas. So we get U is equal to kinetic energy is equal to F by 2 nRT. So the change in energy du will be F by 2 nRT. This is your internal energy. This is your second formula, everyone. That's what I'm saying. The KTG, calorimetry, everything, right, laid the foundations for this. Got this? The third one, work. Where did we learn this thing? Work per energy. So W is integral F dx. We can write force as pressure into AdX, and AdX becomes dV. So work done is integral PdV. Now listen to this thing. This is important. So if you take the area under the curve, so this is also area under the PV graph. Now since pressure and volume cannot be negative, the graph will exist only in the first quadrant. So how do you decide the work is positive or negative? So if you have a PV graph, and if this was the process going from A to B, the work done under the graph is the area under the curve. Now see, when you're going from A to B, is the volume increasing or decreasing? Volume is increasing, so dV is positive. So the arrow will tell you whether the work is positive or negative. Normally it used to be area above the x-axis and area below the x-axis. That doesn't work here. So area under PV graph is work. So again, the sign convention here. So let's say you're going from left to right. So the work done is area under the curve. You can clearly see here volume is increasing. So dV, pressure is always positive. So dV is greater than 0. So work done from A to B is positive. So be careful with that arrow there. Suppose the same process is going like this. So this is B and this is A. You're going in the reverse. So when you go from B to B, the volume decreases. dV is negative. So work done when you go from B to A is negative. So the arrow will decide whether the work is positive or negative. All clear with this? So that arrow is important. Any doubts on this? What is a cyclic process? So cyclic process is if a gas undergoes different processes and comes back to the initial state. We say it is a cyclic process. So for example, if someone gives you a figure like this, how do we calculate the work for this? So listen carefully. What we can do here, I'll split the graph into two parts. The upward going part, A to B, and the downward part, B to A. So when you go from A to B, what is the area under the curve? The area under the curve, this entire thing is the area under the curve. So this area is, let's say, A1. So when you go from work done A to B, the arrow is from left to right. So this is plus A1. When you go from B to A, what is the area under the curve? The area under the curve is this. Let the area be A2. Since you're going from B to A, the volume is negative, dV is negative minus A2. Now, if I add these two, what do you get? You get the area enclosed by the curve, isn't it? So in a cyclic process, the area enclosed by the curve is the work done in a cyclic process. So work done in the cyclic process is the area enclosed in the curve. In this case, which is A1 minus A2. Is that clear, everyone? So if someone gives you a closed figure, you just find the area enclosed and yeah, you're done. You'll get the work done in a cyclic process. But again, how do you decide whether it is positive or negative? Sign convention matters again. But any doubts on this? How do you define the area? Clear, na, Ashvi? Clear, Ashvi? Shreyan? Pratyasha? Ishman? Utsa? Trishi? Clear? Sign convention here. Now, this entire thing is reverse in chemistry, so be careful. So let's say we have a process. The arrow is this way, going clockwise. Just look at this thing. So when you go from A to B, your volume is increasing at a higher pressure, but your volume is decreasing at a lower pressure. So clockwise is positive work. This is the explanation. When you go from A to B, volume increases at a higher pressure. So integral P dV, P is high, dV is positive. You can clearly see that from the previous graph, A1 is bigger than A2. From B to A, volume decreases at a lower pressure. So clockwise is actually positive direction. So be careful. Don't use your right hand thumb rule. It doesn't work. That is the better way to remember. Instead of the sign convention, if you're confused, think of like that. The same graph, if you have arrows like this, so anti-clockwise is negative. You're expanding at low pressure and you're compressing at high pressure. Clear with this? So there, that is a little about the work. Clear, everyone? Now, here, if you see, the work done and the heat depends on the process. So if you're going from A to B in different processes, they are path dependent. Whereas internal energy is independent of, depends only on the initial and the final state. Change in internal energy. This is a state function. If you say I'm going from A to B and did not ask you how you're going, this is called a state function. So in all these processes, delta U AB, delta U2 is equal to delta U3. They're always equal. Doesn't matter how you go from A to B. All clear with this? Great. Let's do one or two easy ones and then see. PV graph, and let's say we have a curve like this. This thing looks like semicircle. This is A, this is B, V naught, 2 V naught, P naught, 2 P naught. This is N moles of gas of helium. Find work done from A to B and work done from QAB. So when you go from A to B, find the work done and find the heat. Let's get this thing. That looks like a semicircle. What does it even mean? I think we discussed this thing in work per energy, remember? Yeah. Suppose if I give an fx graph and if I give a semicircle kind of thing, is this actually a semicircle? If I change the xk units, won't this thing stretch?
Yes, sir.
This is an ellipse. If your quantities on x and y axis are different, then this is not a circle. This will be an ellipse. So the formula you have to use is not pi r square. You have to use pi ab. Do you guys remember like that? I think we did something like that in work per energy. I don't remember we did.
Sir, we did.
We did ना याद था ऐसा कुछ किया करके. Mm, mm. We did a lot of weird things. Must be there somewhere. I'm not remembering. Okay, no probs. We'll do it again here. So this is the idea there. So the shape here is actually an ellipse. So keep that in mind. Since x and y axis have different properties or different quantities, if you take pi r square, what do you mean by r there? It doesn't make sense. If x and y are both are pressure, then you can say it is a circle. So you need to know this formula in case you forgot area of an ellipse. A is your semi-major axis, B is your semi-minor axis. Area will be pi AB. You will need this. There, now get it. Find the work done from A to B and find the heat from A to B. Nee, Param, that is wrong. Nee, Utsa, that is wrong. Right, Arya. Try. Take a minute, it's a good one. Four plus. Okay, that's overall by four, na? Right. Okay, let's see. Look at this thing. So this is an ellipse. Basically, this is an half ellipse. So this should be your major axis, which is 2a, which is equal to v naught. So a is equal to v naught by 2. This should be your minor axis, b, which is equal to p naught. So this can be divided into, you need to find this area. That's an half ellipse. And you need to find this area, one rectangle. So this area will be p naught into v naught. And this area will be pi AB by 2 because it's an half ellipse. Pi A will be V naught by 2, so that is pi P naught V naught by 4. So therefore, the work done to go from A to B, it is plus because you're going from left to right, and it is P naught V naught pi by 4 plus 1. That's your work done, everyone. Next thing, what is the temperature at A? P naught V naught by NR. Temperature at B, 2 P naught V naught by NR. So from here you can find the change in internal energy U to A by B is equal to F by 2 NR delta T, which is TB minus TA. Helium it is 3 by 2 number of moles are TB minus TA is P naught V naught by NR. So UAB will be 3 P naught V naught by 2. From thermodynamics first law, delta Q is equal to work done plus delta U. Just add them up. You will end up with P naught V naught pi by 4, that is 1 plus 3 by 2, that's 5 by 2. That is how you get the heat. Clear how we did this thing? So work done, find the temperatures, use that to find internal energy, then use the thermodynamics first law to get delta Q. This is how the questions will be framed. Yeah, I think most of you did get. Please check. All clear with this? Any doubts on this? there. So that would be the last one for that day. So next class when we catch up, right, we will continue from here. We will do more models. So next class will be primarily that only. Like, we will be discussing all different kinds of processes, isobaric, isochoric, what is work done. So in everything, the theme is same. We will try to find the work. We'll try to find delta U. We'll try to find the delta Q for each process. So we have some really good problems like efficiency of a cycle, heat engines, and all that stuff. So we will take another 2 classes, maybe 2.5. Not a tough chapter. Like I said, as long as you remember your formulas and your standard things, you will get it. So that is one. And next thing, this thing, I just wanted to show you something. Your seniors, that day I took a meeting, right?